Okay, gang, good morning. Happy Friday. Today, our 33rd class, we're going to cover Taylor series. It is just an extension of the Taylor polynomials that you worked with last class. I just handed back quiz number 5. The results were generally pretty good. Keep in mind that the quiz is a very low stakes way for you to get feedback. You had to write 5 proofs essentially on this one, and it's expected that you're going to make some mistakes along the way. So don't just take that quiz and shove it in the back of the folder, never to be looked at again. I wrote some comments on there, so take a look at my comments, figure out how to write these things up. If you want to show it to me another time, just informally show it to me. The goal is to figure out, how to say all these things in the proofs before the test. That's the high stakes thing. This is low stakes, okay? All right, but generally, good work on the quizzes. I know people are working hard. Currently, you should be polishing up project number 8. That is due on Monday. And then I think a week from today is test number 3. So Friday coming up. Questions on the calendar. Okay, then let's get started on page 54. In this class, we investigate Taylor's series. We'll look at what happens to Taylor polynomials as the degree approaches infinity. Okay, so we saw this crazy formula last class. In fact, you should hopefully have believed this crazy formula was reasonable in your work in last class, where we had the given function like e to the 2x, and we tried to approximate it with a polynomial by equating all the derivatives, right? And this is the formula that we end up with. Just a reminder here, how much is 0 factorial? 0 factorial is 1. Don't be frightened by that. It is not division by 0. It is division by 1. This over here, this crazy symbol is, I don't know, some typographical error. It's supposed to be just dots in between them, okay? All right, so here's what we're going to do. We're going to find the Taylor series for f of x equals e to the x near a equals 0. And the only difference between what we're doing here and what we did last class is that this is a series, meaning it goes forever. And last class we found the Taylor polynomial of degree 3 or 4 or something like that. So we're going to go forever. Okay, let's give this a shot. Here is how I like to write things up. You are welcome to write things however you wish, but there's just a lot. We're going to use that formula, and there's just a lot of things to keep track of in that formula. So I have a way to write things out that helps me keep track of all these pieces. All right, so the first thing I'm going to write over here, f of x, and f prime, and f double prime. We'll do 3 of them here. The nice thing about e to the x is that when you take all these derivatives, they stay exactly the same. And then we are going to plug the magic number into each of these things, and the magic number is given right here. Right here, a equals 0, right? We're just going to plug 0 in. How much is f of 0? 1, right? E to the 0 is 1. Now we're going to plug 0 into all of these derivatives. And how many you need to do really just depends on how long it takes to recognize the pattern. So just do enough to recognize the pattern. The pattern for e to the x is really easy, so we don't have to do that many. But if you feel like you've got more complicated thing in front of you and you don't see the pattern after 3, do a 4th derivative, do a 5th derivative. What are the values of all these at 0? All 1s. Okay, and now I'm going to point out that, for example, the coefficient up here of the x minus a cubed term is the f triple prime divided by 3 factorial. So it's the f triple prime divided by 3 factorial. I'm going to write something up here that is just mathematically incorrect. So it's not like such a great thing to write, but I'm just too lazy to write it the right way. I'll put in a different color to show you it happened at a different time. I know I'm supposed to take that guy and divide by 3 factorial. And I'm supposed to take this guy and divide by 2 factorial. And this one over 1 factorial, and this one over 0 factorial. So when I say I've written something's not true, is f triple prime of 0 equal to 1 over 3 factorial? No, it is just equal to 1. But I'm starting to build this stuff in the formula, and I don't feel like writing it all out again. Okay, so that means now we're just going to do the calculations. How much is 1 over 0 factorial? That's just 1. 1 over 1 factorial is also 1. Now things change. 1 over 2 factorial, 1/2. And 1 over 3 factorial, 1/6. And then the last thing, now that I've got my coefficients, for example, this thing circled up here in purple, f triple prime of a over 3 factorial is 1/6. And now I just have to tack on the x minus a to the right power. So put it here in green. X minus, how much is a? 0. So you don't actually need to write it, but I'll put it there. Normally you need to write it. And then what's the power on this one? Is third power. And it's just convenient that the power matches the order of the derivative, also matches the factorial. Whoops. So that's multiplied by x minus 0 squared, and x minus nothing to the first, and x minus nothing to the 0. And all we have to do is put plus signs between those terms, and we've got our series, right? So we'll do it down here. E to the x equals, first term simplifies quite a bit. What is it? It's just 1, right? X minus nothing to the 0 is 1. Now we're putting plus signs. The next term is just what? X, right? Just 1x. Plus, next term, x squared over 2, plus x to the third over 6, plus dot, dot, dot. And so when I say e to the x equals, I really mean equals, but only because I put in that dot, dot, dot. It's not equal when you go up to x cubed, and it's not equal when you go up to the x to the 100th, but it's equal if you go forever. Okay, so all of this is largely new. Largely old. We did this last class, but the way that I like to organize things is maybe new, and if that works for you, go for it. I don't need to see you write it out like this. I just need you to get here. Because there are so many pieces, I find it helpful to kind of orderly, systematically list all the pieces separately before I gradually get to my final answer. Okay, but then the kind of new thing for today is the general term. Because we're going out forever, we want to try to capture the pattern in general. Now remember, this was the 0 term, and this was the first term, and this was the second term, and this was the third term. And what we're after here is the nth term. N is our letter for the general term. So we just have to capture the pattern as best we can. X to what power? X to the n for sure. Divided by, what's the relationship between the purple number and the denominator? It's that number factorial. So what am I putting? N factorial. Plus dot, dot, dot. Again, I got to make sure it goes forever. So that's the general term. And figuring out that x to the n over n factorial is sometimes tough. It's what you're doing in this project that you're working on. You got a few terms in front of you, and you have to try to generalize and capture all of the patterns. And so then if we want to write this thing in compact sigma notation, let's do it. So we've got our general term there, x to the n over n factorial. N equals, yeah, what's the 0 is n, right? So x, n equals 0 all the way up to infinity. So that right there is the Taylor series for e to the x about a equals 0. Not a whole lot that's new today compared to last time. Just writing the general term, maybe slap a sigma in front of it. They're not always going to be as easy as e to the x, but we got to start somewhere. Okay, so that's groovy. Now this is a series, right? This is a power series because it's got x's in it. And we saw, not last class, but 2 classes ago, Monday, that power series have intervals of convergence, which means that maybe this series here does in fact converge to e to the x for x between like -5 and 5, but then maybe outside of that it diverges, right? It's an infinite series, a power series. It might diverge for some values of x. So at this point, we're going to find the interval of convergence, and we're going to do this just like you're doing the stuff in the project. What test do we need to use for every power series? Is a ratio test, right? So let's use a ratio test. Ratio test. Here we go. Limit. N goes to infinity. Big absolute value, big fraction. Does the general term go on the top or the bottom? It goes on the bottom. So downstairs I've got an e. Nope. Downstairs I have an x to the n over n factorial. And then upstairs we just have the next term, right? The n plus 1, replacing all those n's. So it's x to the n plus 1 over n plus 1 factorial. Limit, n goes to infinity, absolute value. What's our standard technique for cleaning up this fraction in a fraction? Multiply by the reciprocal. Good. Thank you. Okay, let's start canceling. What happens with all these x's? Just get x on the top, right? There's one more x up there. What happens with all of the factorials? N plus 1 on the bottom. Good there. And then oftentimes we would take this x outside with one little adjustment. What's still on it as it's out there? Absolute value, right? It's not just x out there, it's absolute value of x. But in this case, the limit is one of two special cases you might see when doing the ratio test for power series. N going to infinity, x appears to be a variable, but it's just some fixed number, so it has hardly any impact. What is this limit? It is 0, right? Because the bottom is getting bigger and bigger, and the top is just sitting at some number. That limit is 0. And when we do the ratio test for a power series, we say, hey, we would love to figure out where the thing converges. And the ratio test says if that limit is less than 1, then the series converges. And so normally there would still be x's here, like maybe something like this. Maybe it's like 2 absolute value of x is less than 1. Like maybe that's what it looks like. And then you do your, like divide by 2 and then -1/2 and +1/2. But in this case, 0 is always less than 1 no matter what x you pick. So what is the interval of convergence here? Minus infinity to infinity, right? This thing converges, that series converges for all x. So that is our interval of convergence. So the radius of convergence is infinity, which is really good news for us because usually when you're doing ratio tests on power series, what else do you have to test after you've done that? Endpoints, right? You have to do them just two completely separate series to consider from scratch. But in this special case, no endpoints. Okay, one last thing for this guy before we move on. If you plug in x equals 1, just for kicks, if x equals 1, the left-hand side is just e, right? And the right-hand side, we'll just write out a few terms. 1 plus 1 plus plus 1/6 plus dot dot dot, where again the numbers in the bottom are factorials. In fact, I'm going to go back and write them as factorials just so we can really see the pattern. This was 1/3 factorial. 2 is the same as 2 factorial. What's really under here is a 1 factorial. What's really under here? 0 factorial, right? And so if you type in the sum of those fractions on your calculator, and the more you do, the closer you actually get to e. It just gets, it approaches e from underneath and gets closer and closer and closer. In this case, it's e to the first because I picked x equals 1. When I was in, I think I was in high school, I had a pencil that that had this thing written on it, e equals 1 over 0 factorial plus 1 over 1 factorial plus, and I don't know how far it went, like 12 or something, like however many you could fit on a standard pencil. But every time I sharpened it, the approximation got worse. It was so disappointing. Okay, next page. There is an explanation. I'll tell you during the activity. Yeah. All right, let's move on here to number 4. Because that's quick. Yeah. All right, let's find the Taylor series for f of x equals ln of 1 plus x near a equals 0. We're going to go up to degree 5. The first thing you're going to do in the activity is find the general term, so we're not going to find the general term here, but hopefully you'll see the pattern. As Nick mentioned, the e to the x one is really, really easy. This one has derivatives that are not as simple as the e to the x one. So let's see what happens here. I'm going to organize my stuff in the same way as I did before. Yeah, so we're going to do it here. Typically, I stop writing primes at 3. And so you can put the number of the derivative up there just as a number. This is fourth derivative if you put that 4 in parentheses. So I don't think those are Roman numerals. I don't think they are. Yeah, I don't. Yeah, I don't think you can use Roman numerals. Okay, so just put parentheses around it. Okay, so we've got all of our stuff here written out. I stopped at 5 because in the problem I said we were just going to go to 5. Normally it would tell you where to go to, so I'm telling you to go to 5. Okay, what is the original function? I'm just copying it here. ln 1 plus x is good. And now we're going to take a derivative. What is the derivative? 1 over 1 plus x. And normally the chain rule would come in. In fact, it does come in. What's the derivative of the stuff? It's just 1, so we don't have to put anything. Okay, that's the first derivative. Now, if you're going to do the second derivative, what derivative rule might you apply? Yeah, that's how I think we should proceed. I think we should rewrite this here, because if you leave it in fraction form, you might do quotient rule, which is okay, but it's just bigger and messier than what it will be if we just rewrite it like that. So let's do that. Okay, so second derivative now, stuff to the -1. -1 comes down. 1 plus x to the -2. Again, times the derivative of the stuff gives you times 1. What's the next derivative? To 1 plus x to the -3. What's the next one? It's -6. I'm not going to write -6. Instead of 6, like why is it 6? It's 3 times 2 times the 1. So if you write it that way, you're going to have a chance to see a pattern, because we know we're supposed to divide by factorials in the next step, right? If you write it as 6, you might lose sight of the fact that it's 6 because it was 3 times 2 times 1. And the next one is going to be a -4 coming down, right? And so yes, it's 24, but it's 4 times 3 times 2 times 1. Okay, so in this case, it's what? 4 factorial to the -5. So if you see a 6, it might be in your best interest to write that as 3 factorial. Okay, so we've got our derivatives here written out with x. Now we're going to change all the x's to what number? 0. That was given in the problem. It's not always 0, but it is always given in the problem. So f of 0, f prime of 0, just write it all out. Okay, so let's start plugging in here. ln of 1 plus nothing. ln of 1 is? ln of 1 is 0. Okay, that's fine. And now we're going to plug 0 here. So we go 1 plus nothing. So in the parentheses is going to be 1 every time, right? Because it's always 1 plus nothing. So how much is 1 to the negative 1? It's 1. 1 to any power, 1. So that one is just 1. So the next one, again, the parentheses is 1. 1 to any power is 1. So what is the final answer here? Negative 1 there. Next one. It's 2. Next one. Negative 3 factorial. Again, you could put 6. I'm going to write it as a factorial. Next one. 4 factorial. If you felt like it, you could continue the factorials going up, right? 2 factorial, negative 1 factorial, 0 factorial there. Okay, so far so good. And then we take all of these things, and again, using that big crazy formula from the previous page, we're supposed to divide all those numbers by what? By the factorials. So what does the, let's start at the top. What is the first factorial you're supposed to divide by? Is 0. Make sure you start that guy at 0. And then you just carry the pattern down. Remember, the factorial is supposed to match the order of the derivative. Okay, and again, this is the part in green where I'm just writing stuff on the board that is not true, and I feel guilty about it. Right? Like the fifth derivative is not 4 factorial over 5 factorial. It's just 4 factorial. Okay, how much is 0 over 0 factorial? It's 0, right? That's just 0 over 1. Nothing there. 1 over 1 factorial. 1. Negative 1 over 2 factorial. Negative half. 2 over 3 factorial is a third. Okay, here is where I think we really start to make take advantage of the fact that we have these factorials in blue. What is, so I see a negative sign, I'll put that. 3 factorial over 4 factorial, that's a fourth. 4 factorial over 5 factorial, that's a fifth, right? Just n plus 1 on the bottom and on the top. And it's possible that that maybe instead of having it written that way, like if we had written 24 over 5 factorial, because that's what 4 factorial is, right? 24 over 5 factorial. I mean, it's true, it's a fifth, but I don't know. I mean, like it might not be so obvious that it's a fifth, but it's obvious because we wrote the factorials. Okay, and then we just have to tack on the x's here. So we'll tack them on here. What's the first guy? X minus the a. How much is a? 0. What's the power? 0. And the next one is x minus 0 to the first. X minus 0 squared, cubed, fourth, and fifth. Okay, so I'm going to scroll this off the screen and rely on you guys to tell me what we wrote. So now I'm ready to write my final answer here. ln of 1 plus x equals, that's the thing we are approximating with our Taylor series. What was the first term? Was 0, right? Don't even need to write it. What was the next term? Was just 1x, wasn't it? 1x. What's the next term? Positive or negative? Negative. I'm going to write that as x squared over 2, okay? Negative 1/2 x squared. What's the next term? So I'm going to write that as a plus x cubed over 3. Minus 1/4 x to the 4th, and then we did one more term, x to the 5th over 5 minus dot dot dot. Again, your next task would be to write the general term with ends. This one's pretty straightforward because we've done a lot of good work to simplify. The pattern is apparent, hopefully, but you're going to do that in the activity, so we're not going to write it on the board here. But I will just say one thing here. Do you guys remember the alternating harmonic series? I think we start with +1 and then -1/2 plus 1/3 minus 1/4. It's just a harmonic but alternating time. Okay, and I said to you that some genius named Leonard Euler figured out that the sum, like we knew it converged. Alternating series test was trivial to say the alternating harmonic series converges, but what it converges to, I don't know. But Euler figured out it converges to ln of 2, and I just shared that with you the other class, and okay, you say so. All right, well let's just plug in x = 1 into this brand new series that we have here. So it's good there. For example, if we let x = 1, what's the left-hand side? ln of 2, okay, great. Equals, again, all the x's are 1s. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus dot dot dot. And so, yeah, you don't have to be a genius anymore to see that the alternating harmonic series converges to ln of 2. Okay, so number 5, just kind of bringing things together with our Taylor polynomials and series. What are Taylor series useful for? So number 1, they are how the calculator finds values of trig functions and log functions. The calculator is really good at 4 things: adding, subtracting, multiplying, and dividing, and it can't do anything else. And so any other button on your calculator besides those 4, some programmer has to tell the calculator how to translate the button you pushed into add, subtract, multiply, or divide. So when you type in, for example, on the calculator, sine of some crazy thing here, and it says that. So initially, I thought that the calculator had inside of it like just a table of values for sine, like a massive table. Sine of 1 is this, sine of 1.1 is this, sine of 1.01 is this. But there's no way the calculator has like every possible thing that I could type in programmed in, right? And so really what the calculator is doing is using Taylor series, I don't know how many degrees, like to the 50th or something, to translate, the sine button, which has to do with the unit circle, right, into addition, subtraction, multiplication, and division. And that's it. So the same thing for like ln. We've got an ln of 1 plus x. That, like this, if you want to find ln of 2 on the calculator, just type in these, 50 terms or however many you need to get as accurate as is necessary. And this is all addition, subtraction, multiplication, and division. So this is what the calculator has programmed inside of it for all of the fancy buttons. Even something as simple as a square root. Like if you ask the calculator for square root of 17, it has no idea how to find a number whose square is 17. But there is a Taylor series for the square root of x, and that's what the calculator is using. They can also help us calculate some sums of series. So we just saw the alternating harmonic series goes to ln of 2. And on the previous page, when we did 1 over n factorial, we got e. That's pretty cool. They can help us understand new functions. Next class, if there's time, we'll talk about e to the I theta. And they can help us with some derivatives and integrals. And we'll do some of that next class, too. Okay, activity starts on the next page. I will walk around.